first things first. We talked about how to compose permutations on Friday of last week. How did you find the inverse of alpha? What did you say? What was your process?
It should just be 1, 2, 4, 5.
Yeah.
Why did we get away with it just being 1, 2, 4, 5?
Because it's just 2 terms in it, and it's just one permutation in each one.
Disjoint.
Right. So first of all, these two are disjoint. Alpha is made up of 2 disjoint transpositions. And what does that tell me, first of all? Why is it important that they're disjoint? They commute one with another, exactly. So I can write either one of them before the other, and that makes no difference. What does the fact that these are 2 cycles, transpositions, do for us?
They're their own inverse.
Each one is its own inverse. So you secretly use kind of 2 properties to find this inverse, right? We're finding the inverse of 1, 2, 4, 5, inverse. So what would be the first thing that you would use in trying to simplify this inverse? Shoes and socks. Right. I'm finding the inverse of a product. That's the same as the product of the inverses. So the inverse of 4, 5 multiplied by the inverse of 1, 2. Right? And then you can use the fact that these are transpositions to conclude the inverse of 4, 5 is 4, 5. And the inverse of 1, 2 is? Right. Because they're 2 cycles, they are their own inverses. And then the fact that they're disjoint lets you trade places, if you want to. It wouldn't be incorrect if you didn't, but right. So what we find out here is that not only is every 2 cycle its own inverse, but this product of 2 cycles is also its own inverse, product of disjoint 2 cycles. So alpha has order 2. Great. What if I asked quickly for what would the inverse of beta have been?
16532.
16532. Great. And how'd you get that?
Kept the first term and then reverse the order.
Yes, just read the cycle backwards. 1, and then go to the left. 6, 5, 3, 2. Yeah, great. Okay. Alpha is already a product of transpositions, so there's nothing to do in part D for alpha. But what about for beta? How do you express beta as a product of transpositions? It's a 5 cycle. How do we write it as a product of 2 cycles? So when you express a cycle as a product of transpositions, you tend to use that first slot as like a holding tank. Right? So if we sort of let's look at beta up here at the top of the screen, right? That if the first thing I did was let me try to blot out the bottom here. If the first thing I did was I did 1, well, what would be the first thing that I do in this line of permutations? 1, 2, reading in the contravariant ordering. So the first thing I did is 1, 2, 4, 5, 6. Whoops, I suppose, hold on. Let me write somewhere the permutation we're trying to get to. 6, 1, 2, 4, 3, 5. Right? So if the first thing I did was 1, 2, I would end up here. And now my 1 is in the position that I want it to end up. Right? My 1 is perfect, but my 2 now is out of place. So what do I need to do next, according to this? 1, 3. If I do 1, 3, then this 2 and this 3 are going to change places. The 2 is going to land exactly where I want it. Right? But now in this first position, I'm going to end up with a 3 that I don't want. Right? So what do I do after that? 1, 5, it's going to move my 3 over here where I want it to end up. But it's going to move a 5 over here into the slot that I don't want. And so then 1, 6, that moves 5 out to the 6th slot where we ultimately want it to land. And it moves 6 into this first slot, which happens to be exactly what I want, and so I know I'm done. Right? So what's the shortcut, by the way? Do you see the shortcut for how to write a 5 cycle or any K cycle as a product of transpositions? What are you doing there? Yeah.
Take its inverse and then obviously take the first number and then just 1, 6, 1, 5, 1, 3, 1, 2.
Yeah, so that's one way to look at it. So take the inverse, as we did over here, and then just kind of take as your transpositions the first position in the cycle paired with each successive element in the cycle. And that's if you decide to write them from left to right. If we were to write these from right to left, we would have taken the original cycle, just on 1, 2, 1, 3, 1. So it's 1, 2, followed by 1, 3, followed by 1, 5, followed by 1, 6, and that gives us this notation when we read it from right to left.
Real quick,
Big finish here. Is alpha an even permutation or an odd permutation? And how do we know it's an even permutation? It's an even number of 2 cycles. It's 2 transpositions, and so alpha is an even permutation. How about beta? Beta is an even permutation. So without computing alpha beta, without actually finding what the transposition, well, we know alpha beta is this, right? But if we didn't know that, how would we know whether it's even or odd? So if we didn't know this part, okay, if we didn't know that alpha beta happened to be a 5 cycle, just knowing that alpha looks like this and beta looks like this, if I multiply alpha and beta, how many transpositions will I have altogether? 6 of them. 2 coming from alpha, and then 4 coming from beta.
You
add the numbers of transpositions, right? 2 transpositions coming from alpha, 4 coming from beta. So alpha beta we can write using how many transpositions? I would say at most 6. But yes, also, yeah. But so alpha beta definitely can be written with 6. 2 plus 4 transpositions. Which would mean that it's what kind of permutation? It's an even permutation. So, give me a speculation, an informed guess, hopefully, but any guess will do, really. If I compose 2 even permutations, what do I always get? Even permutation. If I compose 2 odd permutations, an odd composed with an odd, what happens? I might get an even. How about an odd with an even? Odd. So, one of the reasons that we call these permutations even and odd permutations is because their algebra works in the same way as adding integers, right? Even plus even is even, odd plus odd is even plus odd is odd, right? And it's just the correspondence there is the integers themselves are just the numbers of transpositions that are used to make up these permutations. So, if I take within the symmetric group on n symbols just the subset consisting of even permutations, what is part E telling me about the subset of even permutations in the symmetric group? What property does it have, according to part E? Closure. It has the closure property. Because if I take an even permutation and another even permutation and I compose them together, the result is, again, an even permutation. So the set of even permutations has the closure property. What about the set of odd permutations? No, why not?
Because odd plus odd is even, and that's outside of odd.
Exactly. If I compose an odd permutation with an odd permutation, the result is even, which is outside of that subset. So we can't take the subset of odd permutations and expect for it to meet the criteria to be a subgroup. But we can, potentially, take the set of even permutations and consider that to be a subgroup of Sn, because at least it has the closure property. What about the identity property? Does the subset of even permutations have the identity property?
Yes.
It does. Why?
It's 0 transpositions.
The identity is made up of a product of 0 transpositions, or 2 transpositions. If you take any transposition with itself, will give you the identity, right? And so the identity is an even permutation, so the set of even permutations has the identity property. How about inverses? Do we know that the inverse of an even permutation will be even? It's going to be itself. Well, is that always true? So we knew that the inverse of this alpha was itself, but the inverse of this beta was not its own inverse, even though we can write it as a product of transpositions. What's different between this product of transpositions and that one? The alpha one is disjoint. So a product of disjoint transpositions will be its own inverse. A product of non-disjoint transpositions, probably not its own inverse. But what can we say for sure? If I were to express the inverse of beta using transpositions, how many would I use to express this 5 cycle? I could do it in 4 again, right? Just by using shoes and socks, the way we did here, I can write it as the inverse of this, times the inverse of that, times the inverse of that, times the inverse of that. But each of those inverses is again going to be what kind of permutation? Each one's going to be a transposition, an involution, right? So I can write the inverse of beta using 4 transpositions, Because, according to shoes and socks, the inverse of beta is going to be the inverses of these transpositions multiplied together, but the inverse of a transposition is always, again, going to be a transposition, right? Because every transposition is its own inverse. So, the subset of even permutations also meets the inverse property. So what are we able to conclude about the subset of even permutations? If it has the closure, identity, and inverse properties, it's a subgroup. We call it the alternating group.
Did we prove associativity?
Did we never proved associativity for permutations in general? Right.
So then is it a group? Because that's one of our conditions.
It is one of the conditions. So we should have proved that at some point. The fact that we defined the permutations in terms of functions, by their nature, the composition of functions is always associative. It's one of the benefits of studying functions is that we can't, by constructing functions, make operations which are not associative. So yeah, I didn't prove that, which is my bad. But because we define permutations as functions and the operation as composition of functions is always associative.
So I'm just looking at beta, and I'm just wondering if...
Brian's observation is that if we take this same list of transpositions that made up beta, and we just write it again in the opposite order, so 1, 2, then 1, 3, 1, 5, 1, 6, what's going to happen to this pair of 1, 2s here in the middle? Since it's its own inverse, those are just going to cancel. And then I'm going to be left with a pair of 1, 3s that are next to each other. Those are going to cancel. And so on and so on. The 1, 5s cancel.
And so
and
that's
the 1,
kind of
6s.
driven by associativity, right? The fact that we can group those
Yes.
two middle terms together.
Yep, that is driven by associativity. So beta inverse is going to give me the identity. Yep, so that's another reason why we always only need the same number of transpositions to write the inverse of a permutation as we needed to write the original permutation.